this example, we're going to use vectors to determine the outcome of when we've got two ropes. We've got two ropes on the boat and they're heading towards the shore. And this one is an angle of 60 degrees, this rope, and it's the force of 75 newtons, the tension in that rope. The second rope is at an angle of 30 degrees. Now we're talking about to a line straight to the shore. So if you're standing on the boat, we'll say this is to the left, and this one here is to the right if you're standing on the boat looking towards the shore. And the tension in this rope is 100 newtons and at an angle of 30 degrees. So what we're going to do is to resolve each of these two forces in the rope into their I and J components, and then we will add the two together and come up with the resultant, which will be the total force on the boat. So we've got the tension or in the top rope, the blue rope up here of 75 newtons, so we've got R1, and that's equal to 75 newtons. And we've got R2, and it is 100 newtons. And when we resolve them, now we can set up our I and J components, and usually you set it up to a situation where it's going to be quite easy to be able to resolve. So we'll let the I direction being the line that's straight towards the shore, and the J direction will be perpendicular to that. So we're going to resolve both these forces in their I and J components. So R1 is equal to 75 cos. Now the angle is 60 degrees. And the J component will be 75 sine of the angle, which is 60 degrees, and that'll be my J component. We can, using your little triangles that we've got 60 degrees, the magic triangle, we've got 60, 30, and we've got 1, 2, root 3. And we know that the cos of 60 from this triangle, cos of 60 adjacent over hypotenuse is a half, so that'll be equal to 75 times a half I plus 75 sine of 60 in this diagram will be root 3 on 2. And we can probably just leave it as that, 75 on 2. 75 root 3 on 2j. Okay, so that's resolving this vector here into its component form. 75 on 2i plus 75 root 3 on 2j. To resolve this one, we've got R2. Now it's got a magnitude of 100, and it'll be cos of 30 I. Now, if we look at this, when we resolve it, it's going to be a positive I component and a negative J component, because when this is resolved into I and J, it's going to be that direction in the I and this direction in the J. So we put a minus there, 100 sine 30 degrees J, and that will become cos of 30. Now we've got 30 degrees here, cos is root 3 on 2, so it'll be 100 times root 3 on 2 minus 100 times sine of 30 from our diagram, sine of 30 adjacent, sorry, opposite over hypotenuse, so that's times a half. And we'll get 100 root 3 on 2 I minus 50 J. Okay, so we've resolved the forces now into their I and J components, and what we want to do is to add those two, so we can go R1 plus R2. And when we add vectors, we add the I's and components and add the J components. So we've got 75 on 2 plus, now that's the I component of R1. The I component of R2 is 100 root 3. And then the J component will be 75 root 3 on 2, and then minus 50 J. And when we do the work there and work these out, 122.5 I plus 15J. Okay, so that's the resultant of when we calculate that, do a bit of work with the calculator, and we'll get that as when we add the two together. Really what we've done here is, if we have a look at this, and as you know, when you add vectors together, you add tip to tail, and what we've done is actually move this vector here down to there, and we've now got tip to tail, so when we add the two vectors together, the result is from the very start to the very end, and we've actually got a resultant vector that actually goes out. And just by the look of the diagram, even though it's been fairly hastily and not exactly accurately done, it looks like we've got a positive I component going out this direction and a positive J component going up in that direction. So this is our resultant vector of when you add the red vector to the blue vector. We get that resultant vector there. So we have got that as a resultant of 122I and 15J. Now that as a result, that's in component form, but it is probably best now to express that in magnitude and direction. So if you like, we have got a vector that looks like 122 along there. And that's my I. My J vector is 15. And we want to work out the magnitude of that. Now that's simply a right angled triangle. So we can say that the resultant vector, which we'll just call R, will be just equal to the magnitude of this vector here, which is the square root of 122.5 squared plus 15 squared. Just using Pythagoras to actually work out the magnitude of that. And we get a magnitude of pretty close to 125 newtons. And as you know, vectors have magnitude and direction. So we've got to work out an angle theta there. And from the diagram, we know that the tan of theta is equal to 15 over 122.5. So from that we can say that theta is the angle that has a tan of 15 over 122.5, and you can put that in on your calculator and we'll get an answer of 6.9 degrees. So now we state the resultant. So the resultant force and whenever we talk about a force, which is a vector, we've got magnitude of 125 newtons at, now the original forces were to the left and to the right of centre, so at 6.9 degrees left of centre. So whenever you state a vector, you've got to have two components, magnitude and direction, which we've done in this case. So just recapping again, the question asked for the resultant force on a boat when we've got two forces acting on it through the ropes, and we use component form. We've actually resolved each of the two vectors into their I and j components. So we've got an I and j for R1, an I and j for R2. We simply just add the i's, add the j's, and from that we then have to work out our answer in magnitude and direction. So we've got an I and j answer for our resultant, but to get magnitude and direction we need to then go back and calculate just the norm of the vector and then the angle at which it is acting to the straight line. Thank you.